Alright, good afternoon everybody. Didn't think that I'd be standing up here with a microphone. I was kind of more expecting for it to be all the naturalists, so we can pretend to be naturalists for a few minutes. Anyone who asked us during this week why we were on the boat, why we were coming all the way from Ireland, probably got a very mixed response and quite an ambiguous one, we're only over as a holiday. And that's because we had warned our dads and we kind of intended ourselves to come kind of incognito, because the real reason that we were here, we're not illegal iguana smugglers or anything like that. The real reason we're here is because National Geographic has actually sent us here as a prize for winning the Google Global Science Fair last September. So there were more than 100,000 entries for the science fair. It was done online, and then they brought the final 15 to California, where we competed. We went in front of a panel of judges and did a few presentations, and we competed for the title of Global Science Fair Champions, and then we won. So just to start off, there are actually three of us. Our third team member goes to a different school, and they're to kind of work through the holidays. They've got revision courses and stuff. So she wasn't able to join us on this trip, but she'll be coming later in the summer. So to start us off, the most common question that we get is, where did you get the idea for your project? So we got our idea for our project when Emer was gardening with her mom, so she's going to tell us a little bit more about that.
So yeah, basically it's the question we get the most, and normally we give the same answer that we didn't learn off, but we've said it so much that just remember it. But I'll give you the slightly longer one. Basically, me and my mom were not big into gardening, but one day we got a pack of peas free in a magazine or a newspaper, I'm not sure. So we decided to plant them, and like I said, we're not gardeners, so after a while we got fed up with the peas, so mom pulled them out of the soil. And on the roots of pea plants there's these nodules, and we just thought they were diseased or something, and we just threw them away. Then around the same time in science class we were doing plant biology, and I said to my teacher, I asked her what were these nodules. And inside these nodules there's a bacteria, and it's called rhizobium. So this bacteria, it's a nitrogen fixing bacteria. So it forms like a symbiotic relationship with the peas, so they both get something from this relationship basically. The bacteria gets a place to live, and while living there, it helps the peas to grow faster and enhances their growth. At the same time as well, in geography class, we were learning about inequalities, and I think we were focusing on a lot of the famines around the Horn of Africa. So we wondered, because our teacher was saying that in order to end these food crises, there need to be political change, and climate change had a huge impact on it, but also science could make a huge difference. So we decided to see if we could try and aid the food crisis. And because we had just found out about bacteria, we decided we would give that a shot.
Alright, so we knew that this bacteria was kind of like a superhero bacteria. It gave stuff to the plant, and the plant gets things back from it. But the thing is, in all of the research that we've done about this bacteria, it said that it only worked with plants called legume plants. And that's because legume plants send this kind of signal out to the bacteria while it's in the soil. And then bacteria sends a signal back, and it's kind of like, I'm about to move in with you, so get ready, make me a room. So that's what the plant basically does. It creates a little nodule, and then the root hairs begin to kind of curl in. Now by that time the bacteria has gone into the proximity of the root hairs, and it gets kind of taken in by these curling hairs into the plant, where it then begins to aid the plant, and as Emer said, they both get something out of it. And because legume plants are the only plants that are actually able to do this curling hair and to make room for the bacteria, that's why it was also always assumed that they weren't going to work with any other plants. So it was just kind of assumed that this bacteria, it went with legume plants, and that's it. But we were a bit more open-minded. We were only 14 years old at the time, so we had that lovely optimism that comes with youth. And we
It's not like we're old.
so we decided, you know what, we're going to give it a shot. So we chose to do it with cereal crops like wheat, oats and barley, because they'd be more substantial in someone's diet. We decided to start with the germination stage, because there hadn't been any research on that particular area, but also because we were working to a deadline and we couldn't grow up loads of barley crops. We didn't have the space, we didn't have the time, we didn't really know how. Again, we were 14 years old. So we decided to start with germination. So for that, we made our own homemade equipment. If anybody here has a science background, you know, you have incubators, shaker tables, and stuff like that. We completely made a home lab, and we had it in my guest bedroom. So my mom wasn't very happy about that. We had it in my guest bedroom for 3 years. There was a bed in there, but you could forget that very easily because we had put wood over it, and there were these massive like homemade pieces of equipment there. So we basically took over my house and started doing some experiments, and we started with our germination experiments. And so for this, we just applied the bacteria. Very simple, you know, it was just kind of put the bacteria on and see what happens, and that's exactly what we did. We put the bacteria on the seeds, they'd be kept in homemade incubators, and they'd be checked. Well, first we started off with they'd be checked every night. So we were working at that stage with only about 1,000 seeds, but they were done in lots. So we'd have, say, about 300 seeds to check. We'd have about 300 seeds to check every evening, and that involved looking at them, like literally, you know, up here, they'd be up here, and we had a little stick, and you'd be poking through them looking to see if you could find any roots. So that's how we started off, and as you can, like anyone, as I say, from a science background would probably be horrified by this method, but that's where we started out, and then we began to refine it. So then we moved on to our next stage of the germination test.
So this is where things got a little bit more crazy. We decided to look at the seeds every 6 hours instead of once a day. So that meant, I think it was 1,000 seeds per looking at them, and it added up to 10,000 in the end. But that means that we'd look at them at 12 o'clock at night, and that might take maybe 2 hours depending on the day. And then we'd get back up again at 6 to start it again. And then we had to do that for 2 weeks twice. So it was about 4 weeks of just looking at seeds. So I can't say that looking at seeds is very fun, but we tried to make the most fun that we could out of it. But at the end of all this experiments, we found that we'd sped up the germination rate by 50%. So this means that we had seeds germinating by the 2nd day or by the 3rd day. So only a few were by the 2nd day, most by the 3rd. And we were really surprised and we were really delighted with this result. And then we wondered what would happen when we grew them up. So we started with a small scale where we just grew them in little tiny pots, and we had to measure all the lengths of the little, what are they called? Stalks as they grew. And then we would measure their weight, their dry weight. And then we also did a larger one as well, where they grew for longer and they got bigger, and we did the same again. And I think the numbers are escaping me right now, but we looked at, how many seeds?
Our total test population totaled 10,000 seeds or plants. So, and then we took 130,000 manual measurements. So that means we either measured a stalk or we looked at a seed 130,000 times. Which, you know, when you're 3 teenage girls and all of the rest of your friends are out during the summer, like partying or whatever, to stay in and look at seeds 130,000 times was actually, it wasn't as fun as it sounds.
We did have social lives as well. We didn't just look at seeds.
Yes, we did have social lives.
We find that hard to believe.
Anyway, so we did a large-scale field trial, as Emer said, and for this, it was a little bit more complex than just placing the bacteria on the seeds. So we investigated different ways, kind of looking at a commercial setting where if we were to commercialize this, that it could be a treatment that would be applied before you plant the seeds, which would just make it easier for everyone all around. So we investigated the use of different carriers, and we did peat, because you know Ireland is quite famous for its peat bogs, so that was quite accessible. And it had also been recommended in a scientific paper. Sawdust, because cellulose had been recommended. And then one final one, which we thought of when we were doing a science show for kids in our local area, was instant snow. So this bacteria came in kind of a liquid. So what we decided to do, because we needed to make it into a solid, was we just poured some of this liquid into the instant snow, and all of a sudden it just kind of grew up into this kind of snowy bacteria, which was very handy, although we found out that it didn't work, which is a pity, because if it did work, that would be quite cool. So we ended up finding that peat was the best carrier, and we found that we were able to increase the dry mass yield or the foliar yield, of barley plants by up to 74%. So this means potentially 74% more food at the production stage in the developing world, more food, and in the developed world, for commercial farmers, that would be 74% more profit, because this treatment actually doesn't really cost very much. It was very, very cheap. It's just a matter of growing the bacteria. And in fact, many legume plants, as I was saying earlier, are already given similar treatments to take advantage of the known mechanism. But what we had discovered was an unknown mechanism, which we're going to explain a little bit more about.
Okay. I don't know where she's leading into, so.
Yeah, okay. So this, I'm going to be quick because it can get, you can get very bogged down in the science of this thing. But basically, you know how I was saying that the plant sends a message to the bacteria and then the bacteria sends a message back? But what we found was that those messages in themselves, whilst with legumes they only really serve to kind of provide communication, when you work with grass species like Poaceae grass species, which is what we were using, they actually promote growth in themselves. So these messages are called flavonoids and lipo-keto-oligosaccharides. So that's a bit of a mouthful. But anyway, so the Poaceae grass species have flavonoids, and the bacteria releases the lipo-keto-oligosaccharides. And whilst in the legume, in the nitrogen fixing process, that's just used as a signal, in this mechanism which we have discovered, it's actually used to promote the growth. So it promotes growth, and there is evidence to suggest that. However, that this is being with more complex procedures, and what we found is much more simple and much more commercially viable. So obviously there are plenty of implications for our project, and we're just going to walk you through some of them now.
So, like Ciara said, it could have massive benefits. Where we live in Ireland, we live in quite an agricultural community, so farmers are very interested in the profit that could be made, because, I mean, it's their job, it's going to be great. But then also there is, it could really be used in third world countries where, let's say, they might have the best soil. A lot of their seeds die before they even get a chance to germinate, because this is when they're most vulnerable. So by speeding up the germination rate, you can try and get past this vulnerability, which is really handy. And the other thing is, we haven't actually, I say patent, it might be patent, I don't know. Anyway, yeah, it's open source, so we don't really have, I suppose, ownership of what we have found. But it's also handy because a lot of it was already published in newspapers when we did several things, so no one else can get the rights to it either, because it's published out so much. So yeah, it's open source, which makes it a lot more accessible, and people should be able to get it. And yeah. So we've done quite a lot with our project. We started, like Ciara said, when we were 14. We entered our national science fair called the BT Young Scientist, and we won that. And there was some horrible pictures posted everywhere of us, and that was brilliant. And because we won that, we got to represent Ireland in the European Union contest for young scientists. And we won that one as well, and that was pretty exciting. And then we decided to enter the Google Science Fair, because we felt we had put so much work into it, and it'd be nice to get it onto a global platform. But it's opened so many more doors for us. We speak at loads of events. We speak at getting more girls involved in STEM, which is like science, technology, engineering, and maths. We speak at conferences about food security. And I think last November or October, Times magazine listed us as one of the 25 most influential teenagers in the world. That was pretty weird, because it was amongst like really like famous people like the Jenner sisters and Obama's daughters and stuff. And I think Malala Yousafzai, they would have been thinking like, why the hell are we on this list? Who are these girls? But and they used a really ugly picture as well. So yeah.
So like, I guess our story, you know, it goes to show that the small things can make a difference. What Emer discovered with her mom in the garden led to what could potentially provide food for the world when we reach 9 billion people before 2050. So it's quite scary at the rate at which the population is growing, and the thought of having to provide food for them is, for just the population in general, it's a big task. But you know, whilst we are producing more food, there are other problems along the chain. So there's political and social issues with regards to distribution. Because I know, like, the majority of the people in here are American. Would I be correct in saying that? Yeah?
Yeah.
Well, America and Europe consume 80% of the world's total food production. And that's only 25% of the population. So the other 75% of the population is just, it's literally, they're fighting over our scraps. Also, food waste is an incredibly bad problem. The food waste, I think the recent UN statistics were something like 17 billion tons of food are wasted worldwide per year. And if this food wasn't wasted, we'd actually have enough for everyone on Earth to be consuming 2,800 calories per day. And if there's any nutritionists out there, you'll know that that figure is actually enough for every human to be gaining weight. So given that we have enough food for everyone to be gaining weight, it's kind of strange that there are people in the developing world dying of starvation. So whilst our project has shown that from tiny acorns, mighty oaks may grow, it also shows, like Emer says, that science pays. So we do speak at a lot of conferences, and just the countries that we've visited as a result of this project: London, Prague, Lisbon, Brussels, Spain, San Francisco, Switzerland, yes. What did we? Oh yes, sorry. Paris and the Galapagos, which is probably the most exotic one. So it just goes to show, science pays. Any kids out there, there's no shame in being a nerd because it usually pays off. So that's a brief overview of our project. If anyone has any questions, we would absolutely love to answer them. We love to kind of get into discussions about this because it's a topic that we're quite passionate about. And if anybody has maybe ideas about projects, like we're not exactly the source of all knowledge, but we usually know the steps towards making a difference with an idea that you have. If anyone wants advice, or if you want to keep in contact with us through email or anything like that, I think we have some cards floating around. And just thank you very much for coming up to listen to us. It was kind of, we didn't expect to be doing this, but it's nice to see that people actually were kind of interested in hearing what we did. And again, we're not iguana smugglers. We are, the reason we are here is the Google Science Fair.
If this bacterium is in the soil commonly, is it therefore the concentration of the bacterium that helped, or the proximity to your seed? What was special about the treatment that you gave it?
I mean, I would give it to Emer to answer, but like the answer is just yes. Like there isn't a long-winded explanation. It's just yes. It's the concentration and the proximity. That's the difference. Because whilst it's in the soil, it tends to gather around legume plants, and what we're doing is just giving it the chance to cereal crops to take advantage of it. Does anyone have any other questions?
Oh, well, so are there some areas of the world that are missing this particular resource, or is it in the soils everywhere?
So this bacteria would be in all soils, providing that they have oxygen, because it's so it probably might not be in a bog because it'd be quite water. There might be a small amount, but the majority of soil, yeah, it will be present.
I was going to ask that question, but now I have another one. Have you been contacted by any third world representatives about we need it right here now?
We've had some contact with people. Our next step, we've done a little bit of research, which we left out today, but we've done a little bit of enzyme research to see what's happening inside the seed, but we need to do a little bit more of that before we are happy to go forward with it. We have been contacted by a few organizations who are interested in bringing it forward, and we've given them all the information that they require. It's handy because it's online. Google did that for us, which was great. So it's all online, and so if anyone's interested in bringing it forward, they can. And as Emer said, it's handy because it got so much publicity. It was on like a few of the worldwide news stations when we won the Google Science Fair. It means that if anyone tries to patent it, yeah. If anyone tries to claim it, they can't, because you just type in rhizobium, which is the name of the bacteria, or diazotroph, and our faces come up, which is
Wonderful.
yeah, it's not exactly a good thing. But anyway,
So if it grew best in peat, is there a nutrient missing from other soils that help it grow better in different soils?
So with the peat, basically, it's not so much that we grew it in peat soil. It was we needed something to coat the seed in that would carry the bacteria. So that's what we call it, carriers. So we actually coated the seeds in a layer of peat that the bacteria was absorbed in. So then it could go into any soil with that. So it was just kind of a way for us to coat it, because you can do it like in an industrial setting where the seeds are coated, but because we did it all in Ciara's house, we decided to do alternative methods.
But you mentioned that there's a communication mechanism, and that you learned that the communication mechanism itself enhances the growth.
Yeah.
Do you understand what is the communication mechanism, and could that be created in other ways besides what you've discovered?
Okay, hold on to your chairs, okay, because here we go. Alright, so the communication mechanism is actually secondary compounds that are produced by the plant or the bacteria. They're kind of like hormones that you excrete. So the plant is excreting this hormone. The hormone is the flavonoid. And the flavonoid always, from this bacteria, the flavonoid will always initiate the excretion of another hormone from the bacteria, which is the lipoketo-oligosaccharide. So it's kind of like a sugar, in that it's based on an acylated chitin oligomeric backbone. These are really long words, but you know, they kind of roll off our tongue nicely. So it's based on an acylated chitin oligomeric backbone, and it's a little bit like a sugar. But past research has shown that the way in which it works with these particular seeds is that it initiates the production of gibberellins from the alluron layer. So in the seed, in seed germination, there's this little layer on the outside of the seed. And there's these signals on the outside of the seed that when they go into the seed, that's when germination starts. And what this signal does is it makes these things go into the seed faster. So gibberellins are plant hormones again. It's kind of like when they go in, it allows this enzyme called alpha amylase to start making the inside of the seed into sugar, and that sugar provides energy for it to grow. And gibberellins come in naturally, but they can be brought in earlier by the introduction of this LCO into the environment and into the seed. So yeah, it got very sciencey there for a bit, I'm very sorry. But anyway, that mechanism, it can be used realistically. It can be used with any member of the Poaceae grass species. We suspect this is going to have to be confirmed by experimentation. And we want to look more into this mechanism, because if there's a way that, it is known that if you isolate the LCOs from the bacteria, that you can do it also, but that's actually more expensive and more costly, so it's easier to just put the bacteria on it and let it do its thing. But if we know how it works, but it's kind of difficult, you know, this is the most natural way to do it. So if we were going to be introducing it into agriculture, this would be the easiest way of implementing it, because it's just so natural. You put the bacteria on, the bacteria is already in the soil, we're just putting on a higher concentration, and you put the bacteria on and you let it do its thing, basically. Any other questions?
Well, any known side effects or any known things that can go not as you wanted it to go if you were to use this over prolonged periods of time?
Yeah. So the question is any known side effects, and that's actually, I have never got that question before, so thank you very much. This is going to be fun, because some of the questions I've gotten, I tend to say the same answer all the time because I've had it so often. But there are actually no known side effects because of the bacteria. It's actually a soil bacteria, as we said, so it's already there. It's just in higher concentrations, and it's used to initiate the germination faster. And then because the plants don't form nodules, it means that the bacteria doesn't actually affect it any further when it gets into its mature state. So it's pretty handy, you know, the bacteria, it's naturally doing a really good job, which is why we were surprised that nobody had thought of it before.
That's amazing.
Has this germination process that you've developed been reproduced by any other investigators?
So what we looked at with the crops of barley, wheat and oats, well, we actually got rid of wheat in the middle, but basically barley and oats hadn't been looked at before. People have looked at the growth stage of other plants. I know there were studies done on potatoes somewhere. It wasn't in Ireland. And they didn't see any increase in the growth with them. Not a lot of work is done on it because, as Ciara explained, people just presume because other plants can't form the nodules that it won't work with those plants. So it's kind of, I suppose that's why we've gone so far with this project, is because it's something, a very simple idea, but something that hadn't really been done before. Anything else? Alright, okay, thanks.